Okay, I'm ready to start. Welcome class to the third lecture on Matlab and engineering mechanics. Before we start, I'm really curious how the peer review system works for you for the homework. In reviewing the homework assignments and getting feedback. Is there anybody in the class who wants to comment on that, or as a remark, or is say, hey, I'm happy, or no, the system is shit, or anybody?
No,
Yeah.
I got no peer reviews.
You
I
got
got no marks, no grades, nothing.
nothing. So of all the 3 reviewers assigned to you,
Yeah.
nobody did the review.
Yeah, there was nothing.
That is strange. Please write that to me or to the TAs. That is an interesting thing. Oh yeah, for the recording, somebody in the audience said, I got no review, I got nothing. And that is out of the ordinary. That shouldn't happen. You should at least have 2, in a very special case, maybe 1. But any other remarks? Can I see hands for those who are happy with it? And those who really hate the system? Okay, yeah, that's one says hate because he didn't get reviews, but for the recording, most of the audience raised their hands, they're happy. Okay, then let's start with content of today. And we're going to talk about 2 chapters. Chapter 3, that's about interpolation, and chapter 8, that's about Fourier analysis. And again, like every lecture, I want to do it by an example. And this time the example is a case study. So the case study, and the case study is that we have a measured chem profile, and we have to fabricate then the chem which goes by that profile. So we have a measured chem profile, yeah, and the projector is not on. Sorry for that. Yeah, now it should work. Yeah. So a case study is we have a measured chem profile, and that chem is and we want to fabricate that chem. So yeah, want to fabricate it. Now, what are we talking about? So a chem is something like this. We have some shape, and that's rotating about some fixed point, right, in that direction. So this is what we call the chem. And then on top of that we have a follower, and that's going up and down. So something like this. We call this the follower. And then we measure here the motion y. So as a function of this input phi, we have a y as a function of phi. And it can be some nice shape, right? And the case is like this. We measured the profile. We have an old machine, and we measured the chem, and we want to fabricate it before it goes out. We want to have a new chem. So what we do is we just rotate the thing, and then we measure the distance y. So in other words, the graph we get, we have an angle phi and we have y, and so we have a number of dots here, and something like this, I don't know. And then there's a dwell maybe, and it should be periodic. At the beginning should be the end. And then from this data we want to, which is discrete data, of course, because we measure just discrete points, we want to make a nice continuous profile. I have the data here, so let's look at the data. I have the data here. Yeah, and here. So here. So there's some text file, chem.data. Yeah, we can open it with TextMate, whatever. We see then a file. And the contents of the file is percentage, and then it says date file for measured follower rise for a chem follower system, measured in November by Harry D. And then just a whole list of numbers. And that is measured apparently in meters or something like that. Yeah, that's my guess. In meters, the rise of the follower. Now we want to import that in Matlab, and the funny thing is that you can say load com dot dot, and then you should say load, of course, not load, and then what you get is you get in your workspace by magic an array of 120 by 8 of double, which are the numbers. So Matlab is really smart. So the first lines where was a percentage, it thinks, oh, that's a comment probably, I'm going to discard that. And then it reads one line a number, and the next line a number, it says, oh, it's apparently an array, and then I put it in an array. So that's a nice way to get in data into Matlab. And you can also write to a text file. So, but now we have loaded our data. So so this is the data. Let's copy it into a vector. So long vector, it's 120 long, and yeah, a lot of entries going up and down. So how does it look? Well, the first step, of course, is that you plot the thing. So you plot cam, and it's discrete points, right? So yeah, so this is the cam. Now let's put a grid on. Grid on, and we see something. So we see it started at 0 apparently, then goes down again, and there's a dwell, it goes up, and then yeah, like a periodic motion. And then the last point is not equal to the first point. That's in a periodic thing because that will double the information. So the last point is here, and then that sort of makes the whole thing complete. Now, to fabricate the thing, we have to interpolate. So if you zoom in, to the figure, then you see, well, these are almost straight lines, right? But here, if we zoom in at this curved section, you clearly see that things are changing. How would you interpolate this? Any ideas?
Sinusoidal function?
Why?
Because it looks like one.
Yeah, but then it probably won't fit here, right? Here it will fit, but here it will not fit. This dwell will not be captured by a sinus. Any other ideas? So you're going for somebody in the audience said sinus interpolation, but it looks a bit like a sine function, but a sinus function. But but that is actually a global way of fitting. Is there maybe a local way of fitting you can do? Any ideas? What happens when you just type plot com? What do you get? Dots or lines? Lines, right. Or in other words, let's keep this, hold on, and let's plot the dots on top of that. So say plot com, the real discrete points, and let's say we do red. And I never know the order, is it red dot or dot red, but and let's put the grid on. So yeah, so this is the figure. Let's blow it up so we have an idea what's going on. So actually the blue line is when you just say plot. And what does plot do? Plot is already an interpolator, because plot takes this point and then draws a straight line to the next point, and a straight line to the next point, and a straight line to the next point. So plot is already an interpolating function for your discrete data. You can see that, well, here it works very nice, but if we go to this curved section, or maybe we should go here to this curved section, if you then zoom in, you will suddenly see that there are kinks. That it's not nice and straight anymore. There are kinks between the lines. And we're not so happy with the kinks. And why are we not so happy? Therefore, we have to go back in theory. So, please go away. Yeah, like this. So in theory, we have to go back in theory. So, okay, we have this function, some function, y of phi. So let's draw an arbitrary thing. And I now locally zoom in on a number of points. So here's phi. We have a point here, and we have a point, and we have a point here. So you intuitively, what you would do is you would say, well, between the points, I draw these straight lines, and that sort of nicely interpolates. Then I can get, and let me make these nice and thick. Then I can get these nice intermediate values. But remember that the cam is part of a system, a dynamical system. And in a dynamical system, we have something like force is mass times acceleration, right? Somewhere. And if we have here the rise of the thing, we need apparently also to be able to calculate what are the accelerations. So if we have y of phi, then we can get, how do we get the speed? Well, we have to differentiate the function to the angle and then times the angular speed, right? And if we want to have the acceleration, the function of that phi, then again we have to differentiate here and then multiply again with the speed, and then we keep this one constant, and then we have to multiply with the acceleration. Or in other words, what we see is that we get up to this, we get the first and to the second order derivative needed to describe accelerations. So let's see how that works for a linear interpolation. So this is this function, and then let's see what is y. Yeah, this is y prime, and this is y double prime. So y prime as a function of phi, and then we have to this point, and this point, that's this point, and that's this way. Okay, for this section, y prime is constant, some constant value. Let's say it's this. The next section, the slope is a little bit less, and the next section, the slope is almost 0. So we have this staircase type of behavior, and so this is. Then y double prime, so the second order derivative, and let's put these points again. Well, how does it go? Well, y double prime is the first derivative of y prime, right? So we have to take the derivative here, and since it's horizontal, in between here it's 0. And from one to the other, what's this? Sorry? Infinite? Somebody says infinite. Yeah, I almost agreed. I would say because it goes down, I would say minus infinite, but it doesn't matter, right? So anyway, we write a spike here, minus infinite, in this point. And then again we continue. Well, here it's 0 again, the slope, and then here again, minus infinite, and then 0. Well, you get the picture, right? We don't know, so in between the second derivative is always 0, and then at the point itself it's plus or minus infinite. Are we happy with that? No, because if this is the case, then if you have a constant speed of the cam, then you get forces which are 0 and then bang, and then 0 and then bang, and then 0 and then bang. So this whole interpolation scheme does not work. What to do? So let's copy the thing. Hold it. We can redraw it. We don't have to copy it. So again, this was the function, right? We started with this, and something like this. So is there another way than linear interpolation to get numbers between these points?
Fourier series?
We could do that, but then you do a global a global fit. And I was just saying, well, I don't want to do a global fit yet. So locally, what can we do? Can we make a higher order function through these points? Say we have 4 points. What type of curve can we fit through 4 points?
Square?
Yes.
Rectangular?
Square.
No?
Parabola, so that's what you say, that's square. So then we need a constant, a linear term, and a quadratic term. So I have 3 data points. In this case, I draw 4. So we can even go one order higher, right? We can go to a cubic function. So locally, and then if we say we start here, we call this S for now, then using these two, the beginning and the end point, and the past here and the future there, with these 4 points, I can make locally here a cubic spline. So cubic. And how does that look? Well, it's something like y of s is then, what did I write? Oh, simply with a and b. A plus bs plus cs squared plus ds to the power 3. And I have these 4 unknown factors, a, b, c, d, but I also have 4 data points by which this cubic thing should fit. And then it nicely captures also the change in slope and the curvature. Okay, now does it work for us? So the first question is, how does the y prime look? Well, that's super simple. You just have to differentiate this with respect to s. So y prime of s is then, well, the constant goes away, right? We get b plus 2 cs, s to the power 3, I forgot, plus 3ds squared. So apparently the curvature is a quadratic function. So still has some nice, let me draw it correctly, because the slope goes down, right? So it's still something like this. Then, and it's curved, because it's quadratic. And then y double prime, so that is then y double prime of s is 2c plus 6cs. So apparently that is then a linear function here. So negative, because the slope of this is negative, so it should be a straight line, something like this. But it's a straight line. No spikes in it, nice continuous second order, and it only is valid within this section, of course. For the next section, you use this extra data point and this, you discard this. And then you march through your figure by fitting every time a cubic spline. And that is actually what happens. Of course, this is then discarded. These parts we don't use. So maybe in the next part, the linear part is like this. So we get piecewise linear accelerations. And I would say this really looks good. So I'm happy with this. So let's see how that works in Matlab with this cubic spline interpolation. So here I have my Matlab. Now I'm going to type everything in this let's load cam data. So we say load com dot, right? And then it goes automatically. Then I want to make a row vector out of it instead of a column. That doesn't matter so much. Let's plot it. Oh, maybe it's good to make also a horizontal axis, the angle, right? So we want to know how many points do we have in our data. So that's the length of this y signal, right? And that we want to make a horizontal axis, and well, it seems logic to do 0 to 2 pi for now. I mean, it can be anything if you say it's but 0 to 2 pi is sort of a standard way of we going around the circle. So I gave it a name. What name did I give it? Oh, phi p. So that is on the horizontal axis. So that's a Lin space. It starts at 0, it ends at 2 pi. And how many points? Well, remember it's periodic, but the last point should be the first point, so we should do here n plus 1. Yeah. And then we just discard the last point, so p is 1 to n. So then we have a horizontal, an x-coordinate, and we have the y-coordinate. So now we can plot the figure. So as a phi and then y. Let's put the grid on, and let's put on it also the data points. So again, I plot it in red, I think, with a dot. Oh, in red with a dot. Yeah. Oh, and I should say hold on this, otherwise I lose it. Okay, let's see what happens. Yeah, okay. Oh yeah. I can type like hell. Again. Yeah, that's exactly what I want. I see nicely my data points, and I see the linear interpolation is okay. That's what Matlab standard does. Actually, to be really fair, I should forget the whole linear interpolation, but for now I leave it because that's the usual way how we plot stuff. Okay, now we want to interpolate. And our machine with 100 points. So that's how our machine works. Eh? So we have a machine to remake such a cam, but it has an index of 100 going around in a circle. So therefore, we're going to do again interpolation, and we have to make the horizontal axis, of course, of these points, which are now differently spaced than the variable p. So again, for interpolation, we call it, usually we say u for the horizontal one. That's a Lin space, 0 to 2 pi, and then you could say 101 points, right? And then again, u is u going from 1 to 100. Okay, now we want to interpolate. And how do we do that? Well, there's a very simple function for that. So I think it's called spline. Yeah. Spline is a cubic spline data interpolation, and that's exactly what I talked about now. Cubic is to the third power. So you can give here, this is the function we have. So we have the original data, x and y, and then you give the horizontal values for where you want to interpolate, and then you get the interpolated value. So as a test, we could just do 1 point, right? So let's run this for now, and we have everything. Now I'm not using the function spline, but I use the spline from the textbook because I'm gonna tinker a little bit with it. But it's essentially the same. So I want to have a value v, which is a spline tx, and then the input were the x values, the y values, and then let's interpolate it at some given value. For instance, at 1, and let's see where we get. We get minus 2.975. So we could, of course, zoom into the figure here, and then see, well, minus 2.975. This is the linear interpolation, by the way, we get here. Whereas this is a cubic interpolation, but it's almost in the same ballpark. Differs not so much. Well, if we can do it for 1 point, of course we can do it for a number of points. So the statement here I copy. Hopla. I copy here, I type it here, and then I put my whole vector u, and then I get my whole vector v, all these results. And then maybe we're going to add that to the figure. For instance, let's add that as points, the interpolated points. And then we can see, is there any difference between this linear interpolation, the lines we automatically get? Or so we're going to plot u, v, interpolated values. And Yeah, I'm colorblind, so but let's try how green looks. Maybe I can read it. You can probably all read it, but okay. Yeah, looks okay, right? So we see. Oh, we see lines. No. Why do I see green lines? What did I do wrong? Oh, come on. Ah, yeah. I see green lines. That is strange. Any ideas? Huh?
Maybe just zoom in a bit. Are you sure that there are lines? They look like points.
This is oh yeah, that's maybe my color blindness. I'm totally confused. Okay, let's zoom in somewhere. No, this looks like a green line to me, right?
But it's not. I think it's just red.
Oh my gosh. Okay, well, we can resolve it very easily by just executing this statement, right? Ah, yeah, so we get nice points. Still, I don't understand. Now, if I say the original plot on top of that, so, okay, I'm going to make a new figure. I have my dots, right? And then on top of that, I'm going to plot the original one, original data, P and Y, and I'm not going to specify any color, so I expect it's going to be blue then. Yeah, that's blue, right? Blue and green dots. It's hard to see, eh? Maybe we should make the dots and the lines all bigger. That sort of helps. So this is H. This is also H. And then what, how do we get bigger dots? Marker size, mark size, marker size. Something? Marker size 12. Ah. Yeah. Well, the is? Yeah, here the is. But the other one, the marker size was a good guess, right? Yo. Yeah, and now again, let's throw away some figures. Ah, yeah, now we're talking. So now we see. So now we can zoom in. Well, on the straight part, you see almost no difference, of course, between the lines and the green dots. But if we go to curved sides, like here, curved part, yeah, now we see differences, right? So the blue line is this linear interpolation, whereas the green dot is our cubic interpolation. So clearly, we see differences there. Let's do it again here. We see we see nice that the interpolation is cubic nicely. It makes this curvature thing. Okay. All very nice, but that was not initially our goal, of course. We were struggling not with the interpolation of the values itself, but with the derivative and the second order derivative. So, although we get a nice interpolation here of the function itself, we also want to have as output not only v, but also v prime and v double prime. So we have to edit a little bit in this function to get more output, because so it cannot be so difficult, right? Because if you know what the formula is for v, for this interpolated value, well, then if you have these coefficients, then the prime is this and the double prime is that. You have all the data. So it should be possible to recast that function. So let's open it. Where is it? Spline TX. So this is the textbook function, and why do I take it? Because it's a lot shorter than the real function, because the real spline takes into account that it can be a matrix and all kind of nice funny things, but this is basically the core of how spline works. So the textbook spline from what is this called, Cleve Moller. Now let's look for the interpolation. Well, if I want to change this function, first I have to give it another name. Otherwise things go horribly wrong. So I'm going to save it as my spline, right? Then I know, oh yeah, that's something different. Okay, so now it's my spline, and maybe it's also good to say my here, and then say changed spline tx. Yep. Bijna goed, almost right. Yeah, changed. Changed. Okay, we want more output, so let's immediately put it there. We want the function v, we want the derivative of v, and we want the double derivative, right? dv and ddv. Yeah, but now we have to create them. Well, the easiest way is to start at the end. So v is somewhere assigned in the function. And if we start from there, we can try and understand what is going on. So where is the assignment of v? That's probably at the end, eh? Yeah, here, v. So v is yk plus s. I don't see any powers of 2 or 3 in here. So what is going on? We were doing cubic spline, right? But I don't see any s to the power 2 or s to the power 3. Yes, there's a very smart thing going on here, and I like to share that with you. So first I pointed out, so it says a constant plus s times something in bracket plus s times something in brackets. So in the end you get s times s times s. So this should be the third power coefficient. This is the second power, this is the linear one, and this is the constant. And this is actually a super smart way to calculate polynomials. It's a minimal amount of multiplications and additions you are doing. And it's also a maximum of accuracy you have. Okay, so this is the constant, so this is A, B, C, and D. Well, then we can easily, now I'm going to make 1,000 errors, right? By saying copy and paste. That's definitely going to create errors, but we'll see. So the constant term goes away, right? And then one power disappears, right? Okay. And then we're almost there, because we also have to add, what was it? A 2 for the quadratic one, so 2 dot, and a 3 for the cubic one, 3 dot. Yeah, differentiate this one, that works. Okay, then we take this one. Again, we're going to create errors. DDV, this one goes away. Yeah, this guy, and then this becomes a 6. Yeah. Should work. Did I? Oh yeah, I forgot to remove brackets, right? This bracket goes away, and this bracket. Matlab tells you also, there's a swirl here. So it warns you, like, you're not done yet. Yeah, apparently now it's okay. So let's save it. Well, then we go to our script. We change spline in my spline. And we have to adapt the output, of course. V, dv, and ddv. Well, let's first run it. and see what we get. Errors, of course. Very good at making errors. TDV. Oh yeah. Yeah. Remember when I said copy and paste is the source of all things? Oh, this typing error. Sorry. Okay, again. Well, the thing runs, and apparently it works. We get about the same picture. I can zoom in again. We're only looking now at the interpolation of the points, not at the derivatives. But let's make a new figure, because we now have new data. We have the first derivative and we have the second derivative, right? So we make a new figure. We plot this second derivative as a function of u dv, and then grid on, and we plot another figure where we plot the, that was the first derivative, this is the second derivative, and we put the grid on. Of course, you can also nicely stack them above each other and with subplots, and yeah, we could do that. Yeah, subplot is actually nice, right? How did that work? I forgot. Help subplot. Creates axis in tilt position. Subplot M and P. Breaks the figure into n by n M matrix of small axes. And the P axis is the current plot. So I want 3 by 1. Because I want to stack them 3 by 1. 3 by 1. And this is the first. And then this is the second, and this is the third, and I make it in one figure. Subplot, subplot. So I get the function value, then the derivatives, and then the second, hopefully. Oh yeah, no. Okay. Ah, we should put a grid on here, right? That's a bit dirty. Let's do that. Grid on. Yeah. Okay, what do we see? Well, we see our original data. Then we see interpolation of the first derivative, and then here the second. Yeah, this is not so nice actually. I was not expecting this. What is going on? Did I make an error? No, this is a flat part, so the derivative is almost 0, and in this derivative nothing much happens, so that's 0. This is up, and then from here it's going down. Yeah, it's negative. Yeah. I mean, I should put labels at it. So a y label is v, and then copy, and this should be dv, and this should be ddv. Let's run it again. So function, first derivative, second derivative. But I'm concerned about this, this very non-smooth behavior. Where does that come from? Should I use more points, interpolation points? No? You say no. Who says yes? Maybe it becomes better if you do a smaller. We can do 200 points. I mean, we can do any points. So let's try, right? 200 points. So this is a 2. By the way, this is bad programming that I have to do on 2 places. You should write m equals 200, and then here it should say m plus 1, and this should read m. Then there's only one place where you have to change. But yeah, and the comment. Oh, yeah. Well, if you do this, then you don't even have to interpolate with m points. And you even don't have to change the command to your script. Yeah? It's little things which make big improvements. Okay. 200. Oh. Less points, of course. 50. We do 50. Doesn't work. That doesn't work. That doesn't work. That's what I always have with these games which my kids play. That doesn't work. Okay, so what is going on? Let's go back to our 100. Any ideas, audience? Yell something. Where is the inherent problem? If things go wrong, you should start at the beginning. What was the beginning? Where did we start with this analysis? What is the first line in our script? So let's look in detail at the data. So what is it with the data? So we can open the file again, or you can print it here. How many digits do we see? Now here we see more digits, by the way. That is sort of, we should go to the file. Okay, open. How many digits? 3, eh? So, or 4, you could say, because I want before the comma. But anyway.
So 4 months long would do the work?
Sorry?
You get more decimal.
Well, how do we get more decimals in this file? We don't have them. So apparently somebody measured the whole thing with some finite accuracy. That's life. I mean, you have some dial thing which you put on it. I call it a clockje. I don't know how it in English is called. And you put it on, and then you just read what's there, and that has just a finite accuracy. And that's the best you can do. But apparently, for the best you can do here, we have some noise in the data, which finally is shown here in the second derivative as a very noisy behavior. Now, I like this also to be smooth. Now, and then the big question is there a way to smoothen out this data? And I'm looking at you. What is the answer? How did you start the lecture? By saying?
I hate it.
The answer was I hate it. Yeah, but that was about homework. I'm talking about the topic of today.
Okay.
What was the first answer you gave? When we looked at the function, you said fit A?
Sine, so
Yes. Now one sign is probably not going to work. But if we take higher harmonics into account, so if we assume that this is built up out of a number of periodic functions, each with a higher frequency, then maybe we can describe this shape. So let's go back to my notes. How is that called? My notes. So as an example, for instance, I have some shape, and who is playing the guitar? Somebody in the audience who plays guitar? Violins, also good. Piano, I'm also happy with that. Any string instrument. So imagine this is a string, and then we pluck the string. Or in other words, we have our hand here, and then we release it. And then the thing will vibrate. And then you can go through the analysis, but the thing will vibrate like this shape, and all the intermediate forms. Well, and you will hear a sound. And what sound do you hear? Well, you hear a grondtone, so the bass frequency, and higher harmonics. Now, why do you hear higher harmonics? Because this is not a pure sine or cosine shape. If you want to describe this shape, this triangular thing, you have to do that with a number of shapes. So you say, well, I start with this sine, and then on top of that I do this double frequency thing in it, and then maybe I put this one, and so you put all kind of higher harmonics. And then in the end, if you add that all up, if you add up all these shapes, then you get this form. But it also shows you that what you hear will be a bass tone, then a first harmonic, then a fifth harmonic, or something like that. And those are the tones you will hear. By the way, that's also one of the homework assignments you will have to do. You'll have to sing a perfect A, you have to record it, do an analysis, and you will see you're not able to sing a perfect A. You will see all kind of harmonics. And the funny thing is, I thought I was doing the 440A, but looking then finally at the recording, I saw I do the 220 actually. But that's a detail. You will see. Anyway, that's a nice homework assignment. For now, let's go to our problem. So we can describe any periodic function with a number of harmonics. Or in other words, how do we write that? We then say we have a function, some y of x, and I have to denote, let's say we call this x. And then we say, well, the y of x is a summation of a number of functions, and you go to n harmonics or something like that. And then you start with a cosine coefficient, so you have the cosine j times x, plus you have bj times the sine of j times x. And you just add that all up. So the first harmonic is j is 1, the second is j is 2, and so you add up all these things. And the trick is, of course, what are these coefficients? Now, the nice thing is that cosine and sine are what we call orthogonal functions. So if you want to know what aj is, then the only thing you have to do is you have to take the summation or the integral of y of x, and you have to multiply then that with this cosine j of x dx. And you have to integrate that over the whole x range, which is usually 0 to 2 pi or something like that. And then the outcome is the a coefficient. So you multiply the function with the first harmonic, and then the number which comes out, that's the coefficient for the first sine and the cosine. And then same for the other ones, of course. That's the y of x times the sine j of x. And this is what Mr. Fourier actually, this is what we call Fourier analysis. Then you can get, given some function, any function, you can get these coefficients, and then you can reconstruct the signal here. And as you can see, if you have the signal y, then y prime is super simple, because that is actually j times this y. Yeah, plus some minus and cosine is okay, I will do it nicely. So the y prime is j is 1 to n. So I have to differentiate this one. I get j times aj, and that's going to be sine j of x with a minus. And this is going to be plus j bj cosine j of x. And if you want to have the double prime, you do that again. You get a cosine j of x, and then you get aj, and you get j squared here, sum, and here you get j squared, minus sign now, bj sine jx. But the thing is, how many times you differentiate, it doesn't matter. It all stays nicely cosines and sines. We don't get any strange behavior due to errors. It always will be smooth. This we can apply to our system. In Matlab, the Fourier analysis is done a little bit different. It's of course a discrete analysis first of all, because we have discrete signals. We don't have these continuous functions. And the second one, in Matlab, it's done like y of x is then you get capital Yj times e to the power, now I have to be correct, j of x times the imaginary number. And then in this yj are actually the a and b, because e to the I phi, remember, was cosine phi plus I sine phi. And then this ij is a imaginary, is a real part of yj plus this imaginary part times I. And so yj is then a complex number. So, and if you do it in Matlab, the output you get is this capital Y, imaginary one. And then you have to fiddle around to get the A and B back if you want to. Anyway, this is a detail, this is not so, you can read that in chapter 8. For now, let's do that analysis. And with respect to time, I'm now going to switch to my pre-cooked example. Yeah. My pre-cooked example is here. Yeah, analyze chem. So again, I'll talk you through the first part. This is identical to what we did on the fly here. We load the chem, we put it in a row vector, we take interpolation, we plot that, the measured data, then we do a cubic interpolation, and then we compare it. And next we show first and second order derivative by my spline with taking higher derivatives, and then we will see the noisy data. By the way, here's a nice way of putting a graph somewhere on your screen at some size. I want to have it like this and not like this. And then finally we will move to the Fourier transformation. We will plot that, and then with the A and B coefficient we look at the harmonics, and we will reconstruct also the signal, and we will derive what are then the function itself, the first derivative and the second derivative, and we plot those. Let's do it step by step. And that's also a nice thing. As you can see, this is green and this is white. It's sections, and it's sections because I use double percentage here. If I delete this percentage, then this is all green. So a double percentage makes it into sections, and that's very useful. You can run then section for section. And then it doesn't go ring through the whole script. It does first part, you can inspect, you can change, second part. So the first section is, let's get rid of all the figures. Do we have any other figures? Yeah, here. Get rid of this guy and this guy. Yeah, okay. So, yeah, we're in another directory. So, measure data. Oh, stupid me. Not run. Section. Run section. So, first section is this part where we, what we already saw, measure data and the linear interpolation. Then we advance in this section, then we run that one. We see interpolated points, and then as we saw, if we zoom in here, that we see differences. Differences here, for instance, between the linear interpolation and the cubic ones. Go back to that. Then we go to the next section. That is where we do the interpolation, right? And then we get this shitty result, interpolated. So we don't see it yet in the function value. The first derivative, we already see it. If you zoom in, you see here already a bit kinky behavior, but apparently the second derivative is horrible. Then move on. Then we go to the Fourier. So we take our signal, we do a Fourier analysis, and then the first thing I do, since these are complex numbers, I plot the absolute value, which tells you something about the magnitude of the contributions. So let's run that. Then we see, of course, 128 points, because that is our initial data. And then we see at the beginning we have some values, and they slowly go down to almost 0. And at the end we have some values. And that has to do that it's complex numbers. So it's always a plus bi at the beginning, and at the end of the row it's a minus bi. And it's formed like that. It's almost like symmetric with the complex conjugated. You can inspect that. That is the y, capital Y. So if we look at the first 5 entries, the first should be a real number. Let's do a transpose. That's a bit. So the first is a real number, and then we get this complex conjugated numbers. And then at the end we will see these numbers. So let's plot end minus 4 until end. So those are the last 5 or 6. I'm not good at this. If it's 10, then 6, 7. Nah, well, whatever. And then you see this number is exactly the same as this number, but then with the minus and the plus, and this number is exactly the same as this number. So they're sort of wrapped around with complex conjugated. Now, if we look at the figure, it means that there's an average value, and there are a few harmonics, but after a few harmonics there's nothing going on. There are no higher harmonics. That's the message. So let's continue. Now we are going to do the A and B coefficient. I have a function here, f to ab. Now let's look at that function. F to ab is a P file. It's not an M file. So what is a P file? Does anybody know? P code is a way to make the code itself obscure, so you cannot read it, but you can run it. And it's part of the homework assignment. I want you and you and you to make that function. So to put in a complex Fourier transform signal and pull out the A and B coefficients. And you can test your script with this script, because I put this one on the website. You can run it, but you cannot see what's inside. You have to cook that up yourself. So, yeah, that's the P file. So here I get the A and the B coefficients, and then I'm looking at the first 10 harmonics, and I plot those. Yeah, so let's run that section. So, as you can see, the harmonic starts at 0. So apparently there's an average value of -2 in the function in the graph. And if you look at it, -2, yeah, it's about right. -2 is probably the average of the whole function. And then the first harmonic has a plus cosine and a minus sign, and then but then the contributions slowly, these coefficients go down to almost 0. So you need very few harmonics to describe the function. It's only, well, I would say up to the third harmonic, and then you're sort of done. I just showed 10 to show that it declines. Then we go to the next section, is where we reconstruct the signal. And that is fun, because we then not only can reconstruct the signal itself, but also the derivative and the second derivative. And then we will see that these are smooth. So as I said, the function is a cosine b sine, and then the derivative is just j, and then sine, and j times b cosine, and minus j squared, and just like I wrote down on the notes. And then we plot them in the figure, I think, on top of the original ones. And then you can see how nicely it is. Yeah, so the red one is this is the interpolated with the Fourier analysis with harmonics. And 10 harmonics is far too much anyway. But here, this is an important thing. We see that this horrible noisy behavior of the piecewise cubic spline is totally gone. And we now have a nice continuous second order derivative of the thing. So this global way of doing periodic functions, this global fitting, is a very nice way to smooth out this error data. This concludes the lecture of today. I talked for an hour, right? See you all next week when we talk about zeros and roots, if I'm right. Yeah, okay.